rotational motion. Guys, we have to break it into the rotational and the kinetic, or the rotational and the translational separately, and look at them both the same. So, rotational kinetic energy is this. K equals 1/2, instead of 1/2 mv squared, let's see, if it's translational, it's going to be K equals 1/2 mv squared, isn't it? Well, this is I, 1/2 I omega squared. Think about why. Remember what we said? We said mass is equivalent here. Mass is equivalent here is inertia, isn't it? And velocity's equivalent is omega. So they are the same equation, just in rotational form. So 1/2 mv squared becomes 1/2 I omega squared. All right. Then it says analyze systems with moving axis of rotation. If the body has both translational and rotational motion, like a wheel on a car or like the disc we saw rolling down, Newton's laws for rotation still remain as long as the axis is in the center. If it's not, that's weird. And the rotation doesn't change direction. Okay? So the total kinetic energy for a rigid body is K translational plus K rotational. So this is 1/2 mv squared plus 1/2 I omega squared. So we take the translational part plus the rotational part. Now when you see it, does it make sense that as the rotational part goes up, the translational part must go down, right? Does that explain our ring and disc race results? For the ring, this part was bigger, so this part was smaller than for the disc, right? So the more energy it expends rotating, the less it has to translate. All right, soccer ball with mass m and radius r is rolling at a speed v. Find the total kinetic energy. And it gives us the moment of inertia. So we know K is equal to K translational plus K rotational, which is 1/2 mv squared plus 1/2 I omega squared. So let's plug in 1/2 mv squared plus 1/2 I, it gave us 2/5 mr squared times omega squared. Well, what is omega in terms of, let's remind ourselves of this. Omega is equal to what? How do we go between translational and rotational? Doesn't V equal omega R? Don't we remember this from the very first thing we studied in this chapter? V equals omega R, A equals alpha R, X or D equals what? Theta R, right? So omega equals V over R, doesn't it? So let's plug that in. V over R squared. So we have 1/2 mv squared plus 2 and 2 go away. So we have 1/5 m And here's the cool thing. We have r squared here and r squared there, don't we? So we end up with 1/5 mv squared. So what is 1/2 mv squared plus 1/5 mv squared? They end up the same, don't they? Doesn't it make sense that they would both somehow end up mv squared? They're both kinetic energy, aren't they? So they need to work out. Common denominator is what, 10? So if the common denominator is 10, times 5 times 5 times 2 times 2. So we end up with 5/10 mv squared plus 2/10 mv squared is 7/10 mv squared, and that would be our total kinetic energy. And notice what went away. Guys, what disappeared here? Radius. Did the radius of the disk matter? Does that explain our race between the big disk and the small disk? Yes, the radius of the disk didn't matter if the inertia was the same. So total kinetic energy does not depend on the radius of the disk. It only depends on the inertia. So let's talk about example B. We've got a yo-yo. Yo-yo is a solid disk with a radius r and a mass m. It's released from rest while the free end of the yo-yo string is held stationary. Find the acceleration of the yo-yo and the tension in the yo-yo string. So, what you have to picture is if you're letting go of a yo-yo, the string is here, isn't it? And the center is here. So if we were to look at forces working on this yo-yo, we've got two forces at work here, don't we? What are my two forces that work on this yo-yo? Gravity from the center, right? F sub g. And what about for the string? Tension. And we've got tension from the string going up. But the tension is at the edge. If the tension is at the edge, it's going to cause the yo-yo to do what? Rotate, isn't it? So it is a force that causes a torque. Remember, a force that causes rotation is a torque. So the tension is a torquing force. So what do we know? This is going to cause torque. As a matter of fact, it's going to cause torque that is counterclockwise, isn't it? That's going to help us find the yo-yo, the acceleration of the yo-yo. Because we know the sum of the forces is equal to MA, right? Well, that's going to be mg downward minus tension upward, right? But we also have the sum of the torques, which is equal to I alpha. Well, what's the force causing the torque? The tension, right? So this is tension times the radius. You know why it's the radius? How far away from the pivot? This is R, isn't it? And this is my pivot, is it not? Isn't that what it turns about? It's the center. So this is going to be TR. I, for a solid disk, is 1/2 mr squared. And alpha, if you remember correctly, is A over R. So guess what we can find here? Let's work this out, guys. TR equals 1/2 MA over R. Do you agree? Oops, not over R. Y'all about to let me do something stupid. M-A-R. Because this R gets rid of one of those, doesn't it? And what do we notice on both sides? What do we have on both sides here? R, so that also goes away. So it's still not dependent on R, is it? It doesn't matter how big our yo-yo is. It's going to act the same way. So the tension is 1/2 MA. Well, guess what? Guess what we can do with that? We can plug it in right there, can't we? So now we have over here MA equals mg minus 1/2 MA. Well, that's pretty handy, isn't it? Well, look what all three terms over there have. M. So they all go away. So we have A equals G minus 1/2 A. So A plus 1/2 A is what? Yeah. So we're going to add 1/2 A to both sides. So we get 3/2 A is equal to G. So A is equal to what? 2/3 gravity? Yes? So A is equal to 2/3 gravity. So it's not going to accelerate by falling straight down. You know why? Because some of that energy that it's losing acceleration because it's what? Rotating. The rotating is slowing it from falling as fast. Doesn't that make sense? The more it does this, the slower it does this. So gravity isn't as affecting as much. So now we're going to take this and plug it back in here. So now we're going to get tension equals 1/2 M times 2/3 G. 2 and 2 goes away, so we get tension is 1/3 mg. All right, so far so good? Going. We've got a solid wheel of mass M and radius R moving up an incline as shown. The speed of the ring is V, so it is a wheel, it's a ring. As it enters the incline, find how up the incline the wheel goes how far up the incline it goes. If it's frictionless, the wheel slips. So if the wheel slips, is it going to rotate? No. This means no rotation. There is no slipping of the wheel. You know what this means? This means rotation and translation. So this is our classical case. This is how we used to do it. When we did Newton's law, we didn't talk about it rotating, did we? We just said it slides up the incline. So that's all we have to do for this. We can do this as mechanical energy initial equals mechanical energy final. Initially, it is 1/2 mv squared, isn't it? And finally, when it comes to a stop, it is mgh. Right? Okay, so we can solve for how far up it goes. We're talking about, we don't know what h is, do we? We want to know how far up the incline it goes. We want to know what h is. So let's solve this for h. First thing we notice is what? M goes away. So to solve for h, we have v squared over what? V squared over 2g is equal to h. So now we know how far up the incline it goes, don't we? Now, what if there is rotation and translation? If there is rotation and translation, we start the same place, guys. But here's the thing. This is kinetic energy rotational plus kinetic energy translational equals gravitational potential energy. We have to do both, okay? So now we have to do 1/2 I omega squared plus 1/2 mv squared equals mgh. So here's my question. Here's a good thought question for you. If it's also rolling while it's translating, is it going to get as far up the incline? What's your gut tell you? Think about it from energy standpoint. Is it going to have to use energy to rotate? So does it have as much energy to translate? No. So is it going to get as far up the incline? No. And that would be a great explanation for a short answer question. It doesn't have. It has to use some of its energy to rotate, so it doesn't have as much to go forward, which means it won't go as far up the incline. This right here is the reason why. So 1/2 for a solid, for a disc or a ring, it's what? 1/2 mr squared. This is v over r squared. That's what omega is v over r plus 1/2 mv squared equals mgh. What do you notice though? What do all three of them still have? They still all have mass, don't they? And what do you notice about the radius? We've got radius squared here and radius that will be squared there too, don't we? So it still goes away. 1/2 times 1/2 is 1/4 v squared plus 1/2 v squared equals gh. So now common denominator says what? This would be 2/4. Do you agree? So 1/4 plus 2/4 is what? 3/4 v squared equals gh. So now this is 3v squared over 4g equals h. All right. We are going to finish these notes up on Thursday. So, trying to think if there's much left. Rolling down an incline. You know what? I will finish these notes and put them on Canvas for you. All right? I will. So you're responsible for watching the last little bit of this and then doing your homework, okay? I need your labs on your torque lab that you did, the angular momentum lab that you did. I need those turned in by the end of the day. Okay? Okay, so I'm finishing up the notes for you here. One of the things you need to notice under the note right here, if you'll read it, it says in the no friction case, only translational kinetic energy is converted. We talked about that. With friction, you get more kinetic energy converted into gravitational potential energy, and the real actually rises more. We predicted less, but more. Ooh. Torque causes the object to slow down, and it's provided by the parallel component of the weight. Okay, since friction causes the angular acceleration to be less negative, then friction points in the positive direction for this problem. So friction is actually working to help it roll further up the incline. So look at what we found here. We said that what would happen? We said that we thought that it would actually go less far, but take a look. This is 0.5 times v squared over g is the height, but this is actually 0.75 times v squared over g is the height. So if it rolls, which, I mean, think about it, take a ball and slide it up something, and then take a ball and roll it up something, and which way does it go faster? It goes further here, right? And that doesn't make sense, does it? But it does if you think about friction working in the other direction. Friction helps. The ball go further. Strange, right? Yep. That's weird. Okay, now let's look at rolling down an incline and talk about what happens in that case. If we're rolling down an incline, we've got a wheel starting, and it's going to roll without slipping down the incline. So what we know is this: find the linear speed at the bottom for the center of mass of the wheel. Okay, so we know mechanical energy initial equals mechanical energy final. Fine. Mechanical energy initial is sitting at the top. That would be mgh. At the top, mechanical energy final. We know it doesn't have any gravitational at the bottom, but it does have kinetic energy rotational plus kinetic energy translational. So that's going to end up being mgh 1/2 I omega squared plus 1/2 mv squared. All right, and we're going to be looking for v. So we're going to have to plug in here. We've got this wheel. We know the wheel is what? 1/2 mr squared. So we have 1/2 mr squared v over r squared. That's omega, right? V over r plus 1/2 mv squared. So we have 1/2 times 1/2, and this of course is mgh. M, and m go away. So we've got gh over here. We've got 1/4. We know r squared, and this is going to be squared, goes away. So we've got 1/4 v squared plus 1/2 v squared, correct? So that is gh equaling 3/4 v squared. And now we're solving for v this time. So we're going to have 4/3 gh equals v squared, and we're going to take the square root of both sides. So we are going to end up with v being the square root of 4gh over 3. So that would be the answer to part A. Now it says calculate the acceleration of the wheel down the incline. Okay, so what's the acceleration going to be to do that? That's Newton's law, isn't it? So we know the sum of the forces is going to be equal to the mass of the ball times its acceleration. That's cool. So we got to figure out what types of forces we've got going on here. So we're going to do free body diagram. So the ball going down the hill, going down an incline, we have mg this way, and we have friction. So it's actually which way? Friction is this way, and we've got the normal force this way. This should be a stroll down memory lane, which means that we need the component of this guy right here, which is, if this is at theta, then this is theta. So we need, this is mg cosine theta, and of course this is mg sine theta. Okay, so let's rewrite this. So we have ma equaling, and the acceleration is down the plane. So we have mg sine theta minus the force of friction. Well, we know that is mg sine theta minus the mu times the normal force. So ma is equal to mg sine theta minus mu times what? Oh, hey, wait a minute though. We don't know what mu is, do we? So hang on. This is going to get us into trouble, isn't it? So let's do this. Let's be smart about this. Hang on. Let's be smart about this and just leave it as the force of friction, because I'm going to think of something that you're not going to think of, which is why I'm going to help you. Friction is the thing that's causing this ball to roll, isn't it? So if we look at this, the force of friction is actually a torque force. So what we know is I alpha equals the torque, doesn't it? Okay, well, the torque is the force of friction times the radius of the ball. I, for this wheel, we said was 1/2 mr squared times alpha. Well, alpha is what? A over r. Okay, so what we're going to find out is that r, all the r's go away. So we actually have the force of friction is equal to 1/2 ma, and that we can plug in right there. That makes this a much easier problem. So now we have ma equals mg sine theta minus 1/2 ma. Add that to the other side, and we get 3/2 ma equals mg sine theta. M's go away, so A is equal to 2/3 g sine theta. So there's A. So that's for part B. Now part C says minimum coefficient of friction required to prevent the slipping down the incline. So in part C, we're looking for the force of friction, which is equal to mu times the normal force, right? Well, force of friction we know is 1/2 ma. Normal force, if you remember from our picture up here, the normal force right here is going to be this mg cosine theta. So this is mg cosine theta. M goes away again. So now we've got A over 2 equals mu g cosine theta, right? Do we know A? Oh, we know A, don't we? A is 2/3 g sine theta. Cool. So we're going to take this and plug it in right here. 2/3 g sine theta over 2 equals mu g cosine theta. That's cool because now g goes away. 2 goes away. So what are we left with? We are left with sine theta over 3 equals mu cosine theta. Okay. Divide both sides by cosine. And we end up with mu equaling 1/3 sine over cosine, which is tan theta. Remember how when we looked at the coefficient of friction, we found out that the coefficient of friction was always the inverse tangent of the angle? Well, now with rolling, it's only 1/3 of that. So the rolling does do something, doesn't it? It affects everything. The fact that it's rolling makes it a much more difficult problem. All right, last but not least, let's talk about work. What is work? If we have R here and we have some force here, Remember what work is. Work is equal to the change in kinetic energy, isn't it? Well, work is also torque times theta, which is also the change in angular momentum. Well, let's look at this. Torque times theta. Torque times theta is going to be Fr times theta. Delta L is equal to the change in angular momentum, right? Or delta K. We could do delta K here. We could do it on this side, couldn't we? Delta K is going to be change in angular momentum, which would be, or delta K would be change, that would be 1/2 I omega final squared minus 1/2 I omega initial squared. Okay, let's get rid of that. So this is kind of interesting right here. So that's pretty cool. So now we have a way to look at this. We have 3 different ways really to look at this, and we can take work and either relate it to the change in kinetic energy, which is this. We can take work and compare it to the torque and the angular displacement, which of course is this. Or we can take work and relate it to the change in angular momentum, which is that. All right, which would be impulse, angular impulse. So this would be J theta, wouldn't it? All right, so there's lots of things that work represents here. So let's look at this. Golf cart wheel has a radius of r and a mass of m. The wheel is brought to rest from an initial angular speed of omega. The wheel turns through an angle of theta before stopping. What is the work done to slow the wheel? So we want to know the work done to slow the wheel. And all we know is got an initial angular speed of omega, and it's brought to a rest. So we know omega initial and omega final. And we know omega initial equals omega. So that tells me that really the definition I want is delta K, according to this up here, right? So what we have is 1/2 I omega final squared minus 1/2 I omega initial squared. This is going to be 0 because we know it comes to a rest. So this is equal to 1/2. If it's a wheel, we know it's 1I is 1/2 mr squared times omega initial squared. Okay? So let's figure out what we got going on here. So the work is equal to 1/4 m big R squared times omega squared. So there's my initial work done to slow the wheel. B, what torque is required to slow the wheel? Well, we know work is also equal to torque times theta. Okay, so torque is then going to be work divided by theta. All right, so we know work, we just found that above, is 1/4 mr squared omega squared divided by theta. Okay, so there's the torque I need. What power is required to stop the cart? Well, power, if you remember, is work divided by time. So work divided by time, we know the work is mr squared omega squared over 4 theta divided by t. So this is going to be mr squared omega squared over 4 theta times t. And there would be my power required to change it. All right.
So you've got some things in here in this chapter that you really need to know. You need to remember what power is that's on your formula sheet. You need to know a couple definitions of work. We need to know that work is delta K, which is this. We need to know that work is T, torque times theta, which is FR theta. And we also need to know that work is change in angular momentum, which is, of course, your angular impulse. All right? Okay. So that's the end of, and I will post the notes, the rest of these notes for you, and you need to do six, 4, and 6, 5 exercises because we're going to go over this stuff, and then on Thursday we're also going to review and practice problem solving. All right? Okay. Let's get busy with that.